We'll start up again, and this is what we left off with. So having now t and v expressed as a sum over the normal coordinates in the system, we obtain the following Lagrangian. And in fact, let me exchange the index here for beta. Doesn't really matter what you call it, but let me call it beta. Because say that we're now interested in finding the equation of motion for theta alpha, normal mode alpha. So you see here that we've obtained the desired equation of motion, where we have a set of n decoupled second-order differential equations for these normal modes. And the spring constant, if you will, here is the square of the Eigen frequency. So a couple of observations about this. So first of all, there's no coupling, so we can say that the normal modes in the system are orthogonal to each other. And importantly, we see that the way we wrote the general form for these normal coordinates previously, like this, is fully consistent with this equation of motion. This is exactly the general solution for a 1D harmonic oscillator. And since these coefficients are unknown and complex, we need in general 2n initial conditions to fully determine all of the solutions here. Because C alpha is an amplitude and a phase, we have n equations. Now, I received a very good question during the break as follows. Why couldn't we just from the beginning identify this sum as a constant and then dividing the entire Lagrangian on this constant and end up with this simple form for the equations of motions? Because the Lagrangian should be completely invariant. I mean, the equations of motion and the physics, hence, should be completely invariant if you multiply the Lagrangian with a constant. So why go through all of this hassle that we did with this sum? Why not just identify it as a constant? Because it is a constant, right? It's the sum of ij. There's no ij here, so we can just discard it. Could we have done this? Well, let's say that we did. So we get something like this for the kinetic energy, and similarly for the potential energy, where C alpha beta is now this. So the only problem with this is that we still have coupled equations at this point, because we don't know that C alpha beta is 0 for all values except alpha beta. So that was the point of going through all of these motions, to identify or choose an appropriate value for this coefficient. But I just thought it was a very nice nice observation that if you can identify constant in Lagrangian, you can just divide it out and perhaps get simpler physics, or simpler equations of motion, the same physics, of course. All right, now we should try to reflect a bit over what we've accomplished here. So why would it be beneficial to actually write the equations of motion with normal coordinates like this, instead of using the equations of motion for eta? Okay, so one thing is that these are uncoupled equations. Anything else? Or put slightly differently, what's the advantage of putting the Lagrangian in this form? Compared to the form where we had somewhere ij, tij, and then eta I, eta j, etc. Is there any advantage? Well, if we write the Lagrangian in this form, then we are fortunate enough to know right away what the Eigen Frequencies are. We don't have to calculate them. We don't have to evaluate any determinant, which could become quite nasty for big systems. In this form, it is obvious that the Eigen Frequencies have to be the coefficient in front of the square of the normal coordinates. So that's a huge advantage. We don't have to calculate the actual Eigen Frequencies. And we'll have a look at an example of this in a little while. So in some cases, it might be a bit tricky to find this transformation from the original generalized coordinates to a set of normal coordinates which allow us to find the simple form of the Lagrangian. But if we're able to do so, if we're able to spot some symmetry, for instance, in the system, which makes it plausible how we should choose a new set of normalized coordinates theta to get this form, then the solution becomes very simple. We know the Eigen Frequencies right away, and we have a very simple solution for the thetas. But we'll have a look at an example of this. So first we'll do a trivial example. Just to show you how this machinery is supposed to work. So we'll have a look at an oscillating particle in 3D space. With a little twist, we now associate a different spring constant for each spatial direction. The kinetic energy is like this. equations of motion obtained like this, simply by constructing the Lagrangian and then using the Lagrange equations. So let's now use this ansatz. Inserted into our equation of motion, we obtain the following that has to be solved. So we may now identify the following determinant as the one that gives us the Eigen Frequencies. And the way I've set up this determinant is that I've considered my T and my V, and then I set up the corresponding matrices. In this case, they are particularly simple. They are both diagonal. But we see here from the general definition of Vij and Tij that we introduced in the previous lecture that V just has the spring constants along its diagonal and T has only the masses. The reason for why these matrices become so simple is that there is no coupling between the different generalized coordinates. So from this, we obtain the following determinant. So we get this characteristic equation for determining the Eigen Frequencies. And I realize this is a massive overkill for solving this problem. But this is just to show you basically how this mechanism is supposed to work. Okay, so we find 3 Eigen Frequencies. Like this. Now, all of this is well known, but the one important observation for this case is that from the very outset, we were fortunate enough to have the generalized coordinates, the Cartesian coordinates, actually being our normal coordinates. From the beginning, we had an uncoupled set of equations. So for some systems, which usually are very simple, the normal coordinates are the same as the Cartesian coordinates, for instance. We'll now have a look at a far more interesting example where this correspondency between the original generalized coordinates, for instance the Cartesian coordinates, are not equivalent to the normal coordinates. we'll actually get involved with free vibrations of a linear symmetric triatomic molecule. This corresponds to a real molecule, for instance, the CO2 molecule. So we have the following situation. We have two atoms here with a larger or more massive atom sandwiched in between them. And the distance here should be, in equilibrium, the same. So it's a symmetric molecule, and it's linear, which simplifies our treatment. So we'll now have a look at how we can use this theory of small-scale oscillations to describe how this molecule will behave, vibrate, when it's slightly out of equilibrium, for instance, by heating the system. Assume that in equilibrium, the distance between the oxygen and the carbon atoms is denoted B. So that will correspond to x01 minus x02, which should be equal to x02 minus x03. The distance between these two points. Now, in our theory, we have defined the deviation from equilibrium, these etas, as the position of particle I minus its equilibrium position. So it's the deviation from equilibrium. So in order to proceed, we should find Lagrangian of the system. And to find Lagrangian, we need to know the kinetic energy and the potential energy. So the question is now, okay, the kinetic energy we can write down pretty easily. But the question is, what is the potential energy? In other words, how do these atoms interact within the molecule? And that is not necessarily a trivial interaction. But in order to solve the system analytically, we'll make a simplifying assumption about how these atoms interact. And we'll justify this on the basis that the deviation from equilibrium is just small. So assume that we have only nearest neighbor interactions with a harmonic potential due to the smallness of this eta I. So by nearest neighbor, I mean that we only have an interaction between the oxygen molecule and the carbon atom, and not any interaction between the two oxygens. for symmetry reasons, the spring constant associated with the interaction between 1 and 2 and 3 and 2 should be the same. And the distance between them can be written like this, in terms of the equilibrium distance. So you see that if x1 and x2, the actual positions of the oxygen atoms, are in their equilibrium configurations, then this vanishes. So there's no potential energy in the equilibrium position. And expressed in terms of our etas, the potential energy looks like this. The kinetic energy takes the following standard form. So we now insert x into this, so that x dot essentially becomes eta dot. So the complete Lagrange function is obtained by t minus v, as usual. And we stated here initially that we're considering a free linear symmetric triatomic molecule. So far, we've taken into consideration that it's linear, it's symmetric, and it's triatomic. So what about the free aspect? What does this mean physically? A free particle. What is that?
No external potential.
Mm-hmm. So if a particle is moving without any external forces acting on it, we know that it's either at rest or moving at a constant velocity. So if we, for now, exclude the possibility that the entire molecule is moving, it means that the center of mass of the molecule has to be at rest. So assume then that we have our coordinate system such that the center of mass vector should be equal to 0 then. Inserting our etas for x, we get this. So this is in fact a condition in the problem, since we have assumed that the center of mass is at rest. And conveniently, it allows us to eliminate one of these coordinates from the problem. In fact, we can express eta 2 in terms of eta 1 and eta 3 if we like. Okay, so far we've expressed the entire problem in terms of the Cartesian coordinates. And as I mentioned to you, if we're able to obtain Lagrangian in the form of normal coordinates, so that we have this theta dot squared minus some constant multiplied with theta squared, then we have a very beneficial situation because we know the Eigen Frequencies immediately, and the solution for these normal coordinates is trivial. So the real challenge is to see or find the transformation from the original generalized coordinates to these normal coordinates. So I don't know, from the symmetry of the problem, do you see any way we can achieve this? It's not obvious, definitely. I believe one can see it more easily with some practice. So let me just give you the answer. We define the following. And I think you'll see as we proceed why this will correspond to normal coordinates. So we have by rearranging these equations, we can express eta 1 and eta 3 in terms of these new generalized coordinates. And eta 2 can be isolated from the center of mass equation in the following way, and hence expressed with QA in terms of our new coordinates. So let's now exchange all of the etas in our Lagrangian with these new coordinates. That should be the kinetic energy part, where I've substituted for eta 1, eta 3, and eta 2. And then the potential energy should be like this. Now, I said to you that you might see eventually why this is a good transformation. So one general rule that you can keep in mind when you're faced with a problem like this, and you want to see if you can find some kind of transformation. Oh yeah.
Is it because of the different vibration modes you get asymmetric and symmetrical solution?
Yeah, we'll get to that, definitely. So as you say, we'll later see that we have different modes associated with these normal coordinates, which actually correspond to symmetric and asymmetric solution. But like I was saying, a general rule that you can keep in mind when you want to see if you can find some transformation from the original generalized coordinates to a set of normal coordinates, which simplify the Lagrangian and the equations of motion, is the following. See if you can find a transformation that eliminates all the cross terms between the original coordinates. Because that's what we want in our final Lagrangian, just a set of independent, uncoupled equations. So if you consider your original Lagrangian and its dependence on the generalized coordinates, see if you can find some way to express these generalized coordinates so that you eliminate all the couplings, all the cross terms between them. So let's see if we have achieved this aim with the following. I can simplify this, or rewrite it, if you will, to the following. So first of all, we see that in general we get cross terms from these squares. But the cross products cancel, because you have different signs here and here. So these are the terms that describe the kinetic energy. There's no coupling between QA and QS. And if we now consider the potential energy terms, we have two squares as well. This bracket here squared, plus this bracket squared. Again, from a square, we get cross products between QA and QS. But since we have different signs in these two squares, the cross products will cancel. So this is the whole virtue of introducing these transformations. So with a little practice, you will be able to see, I think, just by inspecting the original Lagrangian, how you can introduce new coordinates that will cancel cross products. So we obtain that all the cross terms cancel, and to simplify the notation a bit, let's introduce the following parameters. Well, just one parameter, in fact, sorry. The following parameter, the total mass of the system. So this is now our Lagrangian, which is the same as our original Lagrangian, but with a crucial difference that there is no coupling between our generalized coordinates qs and qa. And although we can see already that this system has the same form as two decoupled harmonic oscillators, we can make the equivalence precise by scaling these normal coordinates. So I'm just rescaling these normal coordinates qs and qa in the following way. Like this. So now we can not only find the solution for theta s and theta a immediately, but we also know what the eigenfrequencies are. This is the first eigenfrequency squared. This is the second eigenfrequency squared. So we see that one of the eigenfrequencies correspond to, or seems to correspond to, simply oscillation of one oxygen atom with respect to the carbon atom, as if the carbon atom was at rest. It's just k over m. So it's like the carbon atom is at rest, the oxygen molecule is oscillating. The second one here is perhaps a bit more tricky to interpret, because you have k over m, but then also this total mass of the system divided on the carbon atom's mass. So we'll see what these correspond to in a little while. Okay, so this was one way to solve the system. The strategy was to write down the Lagrangian and then immediately transform the coordinates to normal coordinates. So we got this simple form. That's one way. The other way, which we sketched in the previous lecture, was to just use the Lagrangian with the original generalized coordinates and then calculate the eigenfrequencies from the determinant of this matrix V minus omega squared T. So the alternative method here is to identify the matrices V and T in order to solve the characteristic equation for the eigenfrequency squared. So in order to identify these matrices T and V, keep in mind that this is the general form of the kinetic and the potential energy. So what we need to do is to compare our explicit expression for the kinetic energy, which we wrote down here 15 minutes ago, with these general expressions. And by doing so, we can identify each element. The kinetic energy matrix is still diagonal. There's no coupling between the generalized coordinates, but the interactions between them are now no longer diagonal. So the fact that V is not a diagonal matrix tells us right away that the normal coordinates are different from these original generalized coordinates. This is the determinant we need to solve to find Eigen frequencies. So I've expanded this determinant along the first row to obtain this. And hence, this is the equation we have to solve for omega squared in order to find Eigen frequencies. So, in general, this characteristic equation for the Eigen frequencies could be quite nasty. It's not granted that we should be able to find a solution to it. And whether or not this equation can actually be solved, we'll have a look at in the next lecture. But this is just a point that I'd like to underline before we close now, that this characteristic equation can become quite bad for the Eigen frequency, which again underlines the sort of advantage of just obtaining the normal coordinates right away and writing down the new Lagrangian. All right, thank you for today.